Hi, I'm Thorbjörg. Thanks everyone for being here. And thanks, Sasha, for the opportunity of talking about our work at the University of Cambridge around the induced seismicity at the Bárðarbunga Holuhraun rifting event in 2014 to 2015. So now I'm presenting work from the University of Cambridge, but I'm actually employed at the Icelandic Geosurvey, where I'm a volcano seismologist. So first I want to show you the network, the seismic network we used for this study. So here we have the study area, and we have seismometers surrounding Vatnajökull and also on the ice cap. And here you can see central volcanoes, but you can also see that most of the seismometers are concentrated north of the glacier, where we then have also the highest density. So I will present 1.5 years of data from 2014 to 2015, where over 43,000 earthquakes were recorded in this network. So here, this video shows well the episodic nature of the 2 weeks long intrusion. You can see how little seismicity was during and prior dike intrusion in the caldera. It's just very sporadic, when the major seismicity is taking place within the dike, propagated 50 kilometers until it erupted in Holuhraun. At depth level, seismicity is concentrated at around 6 kilometers. So if you focus in on the northernmost segment, where we have the highest density, you can clearly see that the earthquakes migrate here on the western side of the graben before, and then reaching here on the eastern side before reaching the eruption sites, which are here the diamonds here. So 2 days prior to the eruption, the seismicity was already under the eruptive crater, and it indeed actually propagated a kilometer further than the eruption. So here you can see intense seismicity and the relative relocations featuring very well the very segmented nature of the dike propagation. So here I've plotted the entire rifting episode and with the relative relocation results. So these are cross-correlated travel times of automatic earthquake location, then relatively relocated for those interested. I've split the data up in the intrusive, eruptive, and post-eruptive parts. So in blue, we have the caldera events for clarity, and then in red, we have dike earthquakes. In black, we have triggered events by the dike. The blue diamonds are the ice cauldrons, and then we have the eruption site. So I want to highlight the main features or main observations of the rifting episode. Firstly, I want to say that the dike propagated the 50 kilometers, but the direction of the propagation was mainly dominated by the topography, and only by a little part by the deviatoric stresses. It's been shown that there's a topographic low here in Holuhraun where the dike eventually erupted through pre-existing craters of the last rifting event in the 18th century. So that shows us that that pre-existing weaknesses also play a part in this rifting episode. So in blue, we have the caldera earthquakes, and they're mainly concentrating above 6 kilometers depth. And they outline here the caldera faults. And you can see that the earthquakes, the dike earthquakes in red, are mainly located at 5 to 8 kilometers depth, so below the caldera seismicity. We infer that the caldera seismicity is due to a deflating caldera. And you can see that the dike seismicity is consistent at this depth level throughout the 3 periods. Another interesting observation is that there's actually no shallow dike seismicity under the eruption site. And it's not recorded despite the very dense network. So we want to investigate a bit the local and the regional stresses and the effect that it has on the seismicity distribution. So this is a simple Coulomb modeling using geodetic data from PlayState and others. And you can clearly see that here in the red colors, we have higher stress promoting failure actually in the area close to the brittle ductile boundary, whereas the opening of the dike is the largest, above 4 kilometers. It's actually reduced stresses and not promoting failure, suppressing failure, I would like to say. And if you look at the simple Coulomb modeling of the tectonic stresses, the promotion of failure would also be the highest around the brittle ductile boundary. So if we look at we zoom in on the northernmost tip of the dike, here we plotted the data on top of a simple schematic, and the seismicity at 5 to 8 kilometers depth actually show the lateral extent of the dike, and it's clear from this and the Coulomb modeling that the strength of the crust or the stresses were only great enough at this depth level to be able to promote failure. And you can see throughout the propagation, eruption, and the post-eruptive period that the seismicity stays at the similar depth levels. We also looked into the earthquake source mechanisms. You can tell us about the failure of the crusts. They're all very well constrained, and we only observe strike slip failure on very on planes tightly clustered. So here again, I'll show you a figure of the northernmost segment. It's the left lateral strike slip faulting, shown in green, and it's clear that the main features of the dike are actually only shear, a left lateral shear. Whereas here you can see in the depth view that there are only small areas that experience right lateral failure. In the fault plane solution, you can see that the strike of the planes are highly consistent, but still independent from the strike of the dike, which is more of 20 to 25 degrees. Here, there's another perspective of the dike propagation. So you have here the distance along dike versus time. And the purpose of this figure is to show you that the leading edge of the dike is exclusively right lateral, or all here in green, and that the right lateral earthquakes are only occurring behind the leading edge at some constriction points in the dike path. If we look at the whole dike path, we actually see different dominant strike slip faulting. So I've been showing you figures of the northernmost segment here, number 5. But if we also look at further south, where we see that we have different earthquake source mechanisms. So here, for example, at segment 2 and 3, we actually have dominant right lateral failure, and as I said before, left lateral at the northernmost tip. So it's perhaps a bit peculiar, but it can be explained by the simple schematic. And I'd like to remind you here by the curvature of the Bárðarbunga fissure swarm here, colored in green. So it's turning from about 45 degrees to about 25 degrees in the north. So when we have a dike segment intruding to the east of the rift fabric, we get right lateral promoted right lateral failure, whereas when we have the dike intruding to the west of the rift fabric, we get promoted left lateral failure. So the simple conclusion is that the slip direction is determined by the dike opening, that is the strike of the segment with respect to the rift fabric. So the pre-existing weaknesses do play an important role in what failure mechanisms we do get. This is the whole 2 weeks dike propagation plotted as distance along time, distance along dikes, versus time, and with the propagation phases here shown in grey. You can see that the segmented propagation nature of the dike makes this sort of step-like function. But the purpose here of this figure is that I want to highlight that I plotted at the bottom the Caldera earthquakes. So the magma, as Freystedt said, is thought to come from or has been confirmed to come from the Bárðarbunga caldera to the eruption site in Holuhraun, and the earthquake activity only started 2 hours before, I lost my cursor, 2 hours before the onset of the dike here in the caldera, but it didn't really set off until 5 or so days afterwards, when the dike stalled for about 81 hours. So perhaps pressure built up in the caldera during this dike stallment.
You're at 11 minutes now, okay?
Yes. So this is an overview figure of the entire rifting event. So here we have dike events again, so this is distance along dike versus time, and this is, we here plotted all the 43,000 earthquakes we recorded. So the highest seismicity rate in the dike is during the propagation. And here you see the eruptive phase and the post-eruptive phase. And the earthquakes are color-coded by magnitude, and also the size is relative to their magnitude. Here at the bottom, you see the caldera events. You can clearly see that the high seismicity rate in the caldera is during the eruption, when you have the active subsidence in the caldera, but less so during the propagation. And here you can also see the sheer seismicity rate shows this decline, signaling the end of the eruption, as Freystedt was mentioning. Another important point is that there's a difference between the seismic moment and the geodetic moment observed in this eruption, and it's of several orders of magnitude. So for the dike, we have 2 orders of magnitude different between the geodetic energy and the seismic energy released, where the geodetic energy is much greater. And it's similar to with the caldera with 1 order of magnitude. This actually shows us the importance of a seismic deformation. So then highlighting the importance of interpreting both earthquakes and geodetic data together. And then towards the end of the talk, I just want to mention that what was happening in the caldera. So during the propagation and the eruption, we had a subsiding caldera characterized by normal faulting on inward dipping faults. And then actually after the eruption stopped, there is a new mechanism occurring. The activity is now characterized, so this is data from 2017 to 2018. And the activity is characterized by reverse faulting. So, and this has also been shown with in geodetics that there is a suspected inflow of magma in the caldera. So this is my final slide, and this is a summary figure of the whole rifting episode. So we have plotted here the data. So we have a sort of a cross section here through the whole data set. And then plotted that on top of this schematic. So then we have the subsiding Bárðarbunga caldera here on inward dipping faults. And the seismicity in the caldera is mainly concentrated at shallower levels than 6 kilometers, sort of like indicating where the possible magma reservoir or magma domain is located. And then we have the dike seismicity concentrated at about 6 to 8 kilometers depth. And all the earthquakes seems to be induced at the brittle ductile boundary, where then the stresses are the greatest for the earthquakes to be induced. So yeah, I want to leave you with those conclusions, and I will happily take any questions. Thanks very much.
Excellent. Thank you very much. So there's 2 questions already in the chat. The first is by Sarah.
I can't see the question. Can you read it?
I think Sarah will ask it herself, right?
Oh, sure. I'd be happy to ask it. Can you hear me?
Yes.
Okay. Yeah, I was just curious what code was used for the Coulomb stress change modeling in the Woods et al. 2019 EPSL paper. And then is it open source? Because I'm asking because it looked like it nicely takes into account viscoelastic behavior.
So actually, I don't know which one they used, but it is open source because Cambridge only uses open source software. So my close collaborator, Tom Winder, he did this modeling, and he is actually submitting his thesis at this very moment, or maybe tomorrow. And he can answer that question. Unfortunately, I don't know which code they used. I'm sorry.
Okay, that's okay.
I see that Tom is here. Tom, maybe you can put a link to the code into the chat. That would be awesome. Next question is by Bernd. Could you ask the question yourself, please?
Yes, sure. Well, interesting talk, especially since you have a sick toddler at home. I saw yesterday, so great. You say there's asymmetric caldera collapse. So do you have any clue why the northern rim of the caldera is collapsing that much more than the southern one?
There are like several theories. So we think it seems to be more seismically active first, and then the southern rim is less active. We see there's more geothermal activity in the south. It's been observed. They are cauldrons that have been activated after and during the eruption. So that can indicate that the crust is a little bit hotter, warmer at the southern side. Also, there was a rifting episode in '96 where a dike propagated more to the straight to the south, like in this direction. If you can see my mouse, and that relieved some of the stresses in the caldera.
Sure.
So there's a combination of factors.
Yeah.
But it seems to be, if you can see the dashed line, that is inner caldera fault determined by INSAR, and it seems that the seismicity is mainly clustered around that inner caldera fault.
Yeah, great. Thank you.
Okay, there's time for one last question. Thoralf, you want to ask it yourself?
I can try. Can you hear me?
Yes.
Oh, nice. Yes, thanks for the really nice talk. Just for myself, I'm modeling the tremor. I tried to model the tremor at the Holuhraun fissure. And what is important for me is the width at depth and width at the surface. So can you give an estimate of how wide it is compared at the depth and when it starts to narrow again and how narrow it is? When it goes
You're talking about the dike itself?
Yes, I'm talking about the dike.
So I think actually that Freystein is best to reply to this answer, because that is entirely modeled by the GPS and the INSAR data. We cannot constrain that with the seismicity, actually. We can only constrain the lateral extent of the dike. So Freystein, do you want to answer that question?
I mean, I need an estimate more or less. Or it would be nice to have an estimate when it comes to the width of the dike itself and depth. So how wide is it? Like in 200 meters, 50 meters at depth?
No, we only think it's a few meters. So the opening was about four meters, recorded by the geodetics. But Freystein, correct me if I don't remember this correctly, but I think the dike was modeled only to be 1 or 2 meters wide.
Yeah, and it decreases at depth where it is at the deepest level. It is, as Thorbjörg says, it is narrower than these 4 meters. It is on the order of 1 or 2 meters. So yeah, it is like a very thin sheet that accommodates the plate spreading, we would not expect it to be any wider there.
Yeah.
It is a vertical sheet.
Okay. And that is also consistent with field observations of old dikes in Iceland, that they are actually very thin.
Okay, thank you a lot. Makes sense. Helps me
so that's what we're showing with the simple column modeling. So it's exaggerated at the top, but then it narrows at depth where the opening is, where you have less opening.
Okay,